There's a due?
There are dues. I don't know what they are. It's probably $10 a month. Goes to the bar tab.
Maybe like while we're not streaming, I should do whatever I'm going to do that's embarrassing, like, you know, because we won't be recorded. I'll be like, get all the cursing out of my system now. That was all backwards. Am I on mic? Yeah, Mike's
Yeah,
good.
you're on mic.
Okay, good.
And it looks like you're probably streaming now. So now, without any further ado, I would like to introduce Jay Beale. So please give a warm ShmooCon welcome to Jay.
I like these warm welcomes. This is nice. Hi, I'm Jay. We're going to try to not have too much feedback. That thing's off, so... Okay, so any feedback is me. It's my fault. It's on me. Okay, so... cool. So you'll notice the funky keyboard, the funky Wacom tablet. If it comes down to it, the Ninja wrist braces of doom. Those are for if there are any fights that break out afterwards. They're not actually for typing. If any of you have god-awful tendinitis issues, please see me after. I will give you all kinds of awesome advice, including standing desks, which should be a little higher than this. But they adjusted it for my height. Okay, so I'm going to talk to you about something that I've been finding really, really cool, which is playing with containers. This is something that I've had a lot of fun with, and I'm hoping that what you'll get from this is a little tiny bit of my infectious joy at having found a cool new toy. So I'm going to present a couple different toys here, and one of those is basically looking at what you can do with Docker to add security. Not how to secure Docker, but rather how to secure a system with containers that come either out of Docker or out of LXC, LXD. So how did I get into this? I got into this because, by the way, who's awake in here? Is anybody awake? Because I want to make sure that I speak to the people who are awake, and that I don't throw too much noise that people are still trying to sleep or get over their hangover. Who's awake? Awake again? Woo! And how many of you are hungover? Woo! Okay, ShmooCon is clearly calming down since the last time I spoke here. But Keith Myers tore it up last night, and I can't believe I'm awake. Hungover was not an option for me, but okay. So this is so basically, I come at this from a whole long history of playing with Linux and Unix hardening, and one of the big ways that we harden systems was, that we locked down individual programs was we said, okay, let's take that program, let's strip away root privilege, let's stick it in a chroot jail, let's do this and let's do that. And so what I want to do is do some of that with containers. And the issue basically, anybody not know what a chroot is? Okay, cool. So we take the processes file system. We say, this subdirectory of the file system, that's your new root. You can't see out of that, we hope. The difficulty, so there are a couple difficulties with chroots. One is that maintaining them is a little bit of a pain. But the other is that if the program that's in the chroot manages to get to root access, whether it was running that way in the first place or they find a set UID binary or something that lets them get up to root, at this point the game is trivially over. Compile this and that's your technique. So basically, what I've come around to is looking at using Linux containers, and Linux containers are a whole bunch of changes to the kernel that let you start taking a Linux machine and using it a little bit more like a well-disciplined beast, where you can put different programs in different things and then control those things. Okay, so I'm saying things because I don't want to say containers more than 58, 59 times in this talk. Okay, so the big deal with containers is they're still an evolving technology. I think Docker's getting pretty relatively mature. When we come around and talk about LXD, you're going to hear me talk about how it's very much really, really still under development, and it kind of shows. So Linux containers basically revolve around namespaces and control groups. So namespaces was very like the chroot. In the chroot, you said, okay, I'm going to take a portion of the file system, and I'm going to say that portion of it, that's yours. And the rest of the system can see it, but you can't see the rest of the system. Namespaces says, how about if we just have a bunch of orthogonal things, whether those are file systems or whether those are actually down to process IDs and network interfaces and so on. You can even break that down to users, where you have a set of user IDs that are reserved for individual containers and aren't used and basically aren't used by anything else on the system. They're used by this container, and then you have another container that has a whole separate set of UIDs. The other side of that is control groups. And control groups were basically created to give you a way of saying, okay, I'm gonna, think of what we do with hypervisors. I'm gonna run 5 different things on this system. I want this one to only have this much RAM at most, and I want it to have this much storage space at the most, and I want this one to have this. And it's basically taking what we learned in hypervisors, what we've really enjoyed in hypervisors, and now bringing it just into bringing it into an operating system. So all of this is basically focused. There are 3 purposes for control groups. One was to basically let you do your bean counting. Let you say, okay, well, how much did each thing use? And if you're actually billing people, if you're doing some kind of platform as a service, then you want to bill each customer, or you want to bill the one customer who's running all the different things on this, the right amounts for the right things. Another is basically control. I don't resource control. I don't want to let this part have any more RAM than this. And that's kind of a welcome change, because when I started in this field a very, very, very long time ago, like 15 years, it was, and I know that's not that long ago, but to the college students in here, you're like, oh. But you could take a system down if you just simply wrote a little program that forked itself, and each of the processes that came out of that forked themselves, and they all forked themselves, and the whole system would just be out of PID space, and it was toast. So control groups were kind of a very welcome thing. So anyway, this at the end of the day has ended up with containers. And so a container takes control groups, it takes namespaces, and it says, okay, I can start chopping the system up into these thingies. By the way, turn off your phones. Come on. Come on, I don't get a laugh through that. My own phone. A groan. Anyway, groan. Yeah, we're not awake enough to groan yet. Okay, so containers. So containers are basically that next evolutionary step. Or they're intended as the next evolutionary step beyond virtual machines. The virtual machine was the first way we all started using our hardware a whole lot more efficiently. We're like, well, I've got my web server on that silicon over there, and I've got my mail server on that silicon over there. And yeah, there are times where each of them, don't do as much work, and it might be that one's working a lot harder at when the other isn't, and so on. They really could kind of share a machine, but all the security people say never do that, and how would we manage a system that had that many things, and then one of them could cause the other one to have problems? Well, so we said, screw it. We're going to take one set of silicon. We're going to chop it up into a bunch of machines. We'll emulate 5 or 10 machines per piece of silicon, and each one of those will have its own thing. Well, okay, that means that each one of those has its own kernel. Each one of those has its own virtualized hardware. Each one of those has all of these other little bits of what calls a system a system. Of what calls an OS an OS. And, well, we don't have to do all that. So what we can do is basically say, okay, let's just take one system, and this is what we're doing with containers. Let's just take one system, or in my case, one VM, and start chopping it up and saying, okay, this is the web server is going to run in here, and the other parts of the system are going to run in the rest of the system. But that web server, if it's the one thing on the system that's actually getting talked to from the network. So let's just make it that if it does get popped, maybe they can't get into the rest of the system, and maybe that makes it a heck of a lot less useful as a system. It also means getting to root's a whole lot harder, because there's nothing in there running as root, and we're going to come to that, and I'm going to play. So we're going to be pretty demo heavy. I promise I'll stop doing theory in a second. So many of you, this is a slide where I'm trying to head off questions. Many people are using containers for multi-tenancy, for saying, okay, well, this customer can be in this container, this customer in this container on the same VM or on the same hardware, and no, not yet. I don't recommend that. I don't think it's mature enough. And honestly, part of the reason I say that is because I'm still nervous about the whole like multi-tenancy with hypervisors. InGuardians was one of the first to do a public breakout of a hypervisor. We broke out of VMware a long time ago, and then everybody else did too. But that was that took Tom Liston especially a ton of effort, and now it's trivial. Now it's built into penetration testing frameworks. That's not, you don't have to pay money for that split. So yeah, if you can break out of a hypervisor and there's a heck of a lot more containment going on there. I don't want multi-tenancy here. I mean, you have to understand how paranoid I am. As far as I'm concerned, if I'm using one of the infrastructure as a service things, sure, I'm happy with that. But all those virtual machines, all the virtual machines on that piece of silicon should be mine. Okay, well, most of us don't get that, but I like it. Okay, so there are a bunch of different ways to manage containers. There have been a pile of them. The most popular one lately, Docker, has just been really taking the world by storm. And partly, as you'll see, is it's really fun to use. But I'm going to talk to you about two of these in particular. Docker, which has been around for a little while. LXD, which is kind of Canonical's answer to Docker. They're basically saying, can we do LXC as our container thing, but can we create a daemon that makes it just as much fun to use and able to take our containers and make images and push those images to other places and pull them down and do all kinds of funky stuff. So you'll see that. Part of the reason that I put LXD in this talk was that I like that I'm doing Docker for containment instead of the chroots. Unfortunately, it means I've added another daemon to the system, and I like ripping pieces out of systems, not adding new ones in. So my goal is to say I'd like to actually be running things in LXC where I can do it without a persistent daemon. LXD is a nice gateway drug for that. So I can start out with LXD, which is using LXC underneath, and do it that way. So I like that a lot. Okay, so now I'm gonna basically jump right into Docker. I'm gonna show you cool Docker stuff. I'll talk about how you can use Docker as a security tool, and then I'll get into doing the same thing with LXD. And yeah, let's do it. So, tiny bit more theory. So first, you've got containers. And containers are those kinds of lightweight virtual machines, right? Containers are the things I'm gonna lock programs into. The container has a persistent state. That persistent state is called the image. Think of the image as kind of basically the file system and any other configuration stuff. In the VMware world, that would kind of like containers, the images, the VMDK files, the VMX files. In Docker, here's one of the things that I'm going to get into. One of the things that container technologies brought us is a union-mounted file system. And the union-mounted file system is really fun. You basically get a whole bunch of layers, and you start with a layer, and you can start a machine from it, and that layer you can now basically say, I'm going to make some changes. The changes will exist in this layer, and it's kind of like a copy on write mechanism where the stuff that's in that next layer of the file system in essence overrides anything below. Any changes override whatever's below, but you're only storing that much. So if you want to end up if you say, I've got an image and I want to set up 100 different, 100 containers, 100, think of them as virtual machines, 100 containers that are all running from that image, all 100 containers could run. They'll all be using that plus whatever changes they've made as they run. And so those changes they make as they run will end up being really small. And so it ends up being really lightweight. Okay, so I'm going to do a lot of this in demo format. You're going to see me off of the slides, but I've left a lot of this in slides, and I'm trying to make the slides look a lot like the demo so that you can follow along afterwards. My goal in giving this was to make something that's very useful. So if you were to bust out your laptop right now, or if you were to go back home later on and bust out your laptop and drink some caffeine and try to just wipe the sleep out of your eyes from last night's epic party, right, you'd be able to actually use this and do fun things with it. The cool thing is it actually doesn't take a lot of bandwidth. It's not like I'm going to download a whole freaking ISO or a whole freaking VM. It's going to take forever. Things are much, much smaller. Okay. So got my iPad so that I can see my copy of the slides and have a reference and not fat finger too many things. So let's just start. So this is my RHEL 7 system, which I've got to say is a little, this is a little small. So I'm going to check my resolution and try scaling it. That's it. PowerPoint's screwing with the resolution. So, yep. How's that size? Bigger. Bigger. How's that? Yeah? People in the back, how are you feeling? Okay. I mean, you're supposed to have a little feeling of myopia back there, you know. It's supposed to hurt a little. Come on. For some reason, my Red Hat VM, but not my Ubuntu VM, likes to fall off the network. There we go. Okay, so don't do this at home. You should be running sudo in every command so you get nice logging, but okay. Yay, okay. I knew it was either password 0 or password 1. Security department, the security guys won't let me have password anymore. And that's even when I put a 4 instead of the A, and $signs instead of the S's, and a 0 instead of the O. But they still say that the lead hacks or skiddies will figure it out. Okay, so here we go. So I've preceded this machine. So what's that? Can I make it big again? Is that better? How's that? Bigger, bigger, bigger? Even more? There are open seats in the first half of the room. Unfortunately, I think the person saying that might be the one operating the camera, and that one's a little harder. Okay, so Docker run interactive. Give me a terminal. I'm going to choose what image I want to run. I'm going to say I'd like the canonical CentOS 7. By canonical, I don't mean Ubuntu's people. I mean like the actual one from Docker Hub that is built by the Red Hat folks. So if I ran that command, the first time I run that command, it's going to take a little while. It's going to say, okay, I'm pulling down CentOS 7. And the CentOS 7 it pulls down is not that big. It's like 100 megs. But once I pulled it down once, I get to just keep reusing it and reusing it. And this is, and we'll talk about this with the union-mounted file systems. So I run that, and now I'm in a container. And this container has a really great name, B062DB41. Okay, this is, everyone's going to remember this. This is a droid name. So these are the programs that are in the container. I've got bin bash, which is what I started on it, and I've got the PS that I just ran. So I'm going to hit Control PQ. And don't worry, that key combo's in the slides. Now I'm back in my RHEL system. So, and I was in my RHEL system before, but now I'm out of the container. And if I go looking for my bash shell, that's a good idea. I should run sleep inside it. Yeah, let's do that. Okay, so I will run, let's see, let's look at my Docker thing. So Docker basically goes and gives every container, if you don't give it a name, it gives every container a name. The name is a random adjective and a random famous person. So this is Sad Bannock. So I'm going to go and say, okay, I'm going to attach to Sad Bannock. So Docker attach, Sadbanock, back in, sleep, 10 minutes. Control PQ, except I don't want to grab bash now. So there's my sleep. He's still running. It's a process on the system. The interesting thing for me is like, okay, well, what's the SE Linux context that's running in? Is that my... So the other sleep that's running on the system is running in this context, but the context I'm running in here is svert, and we're going to come back to that later. So anyway, okay, so I've got this image that's running, Sadbanock. Well, let's go and start another one, right? So that's running from the CentOS 7. So I'm gonna go and start another one. Docker run IT, so interactive terminal, okay? CentOS 7, bin bash, okay. Control PQ, Docker PS. So I've got two of these running, Fervent Noble and Sadbanock. Okay, so these are two these are two containers. I really have to, if I say VM, I almost always am going to need containers, but not always. You're going to have to get it from context. If any of you have dated, it's kind of the same. The communication is just going to be that imperfect. We're going to try really hard, but it's going to be that, man, I thought I'd get, yeah. So you thought the college kids who might be a little newer dating would be like, oh, that's what's going on. Okay, so let's do something. Let's make a change in each of these. So let's attach to Sadbanock. Oh, I am sleeping, aren't I? This is what happens when you go off script, damn it. Okay, so I'm going to create a file called foo. And in Sadbanock, I'm going to put the contents J in it. And Control PQ and Docker attach. Oh wait, hey, by the way, this is cool. Docker attach FER tab. There's tab completion on all kinds of stuff here. It makes this really fun. Okay, so now we're in this. Cat foo. There's no foo here. Okay, let's put in, this is not J, into /foo. Okay. So now I've got these two containers, and obviously they're going to have different versions. And I don't want to go back into PowerPoint, so I'm going to pull up a PDF viewer, because I think that won't screw with our resolution. Somebody remind me how to full screen. There we go. Woo! Okay, so this is where we get the union-mounted file systems thing, right? So we start out, the way Docker works is you get layers. And we're going to look at a Docker file later, and you're going to see that every entry in the Docker file basically goes and creates another intermediate layer. And part of the reason it does that is that all of the intermediate layers are basically saved. And they're saved so that you can do something and then start another container and do the exact same things and have it take way less time, because you won't have to wait for a command to complete, because Docker basically keeps track of if I start at this file system and I run this command, I get to this one. Okay, cool. Let's just skip and go to this one. It's called the cache, and it's really neat. But we're going to skip that for right now and basically say this is how the images work. You have an image. It's made up of multiple layers. The first layer in both of these containers, I've started out with that CentOS 7 layer. We're going to skip for this. We're going to skip the next one. I haven't added an Apache server to either one, but then I've got a read-write layer on both of them. And so if I want to, I can basically build whole new I can build whole new containers using any of the intervening layers. And so that's what I've done, is I basically used that first layer. And so now I've got two containers. They're both running from that first layer. They've got a read-write layer on top, and that read-write layer isn't persistent. You can make that read-write layer persistent basically by committing it, and I'm going to show you that next. But right now, this is what we've got. So this is kind of the layer reuse. You can basically have two different images, two different containers. Both containers now have different file systems. They're sharing the bottom layers. So unless we persist it, unless we commit the image, it's not persistent. So let's stop both of these. So Docker PFs to find their names again. Let's stop Fervent Noble. Takes a sec. And then let's stop Sadbanak. You get some really funny names after a while. It's pretty cool. Come on. Okay, so they're both stopped. They don't show up in PS. They do show up in PS minus A. I'm going to commit each of these. I'm going to commit the first one, Sadbanak, and I'm going to call that foo is J. And I'm going to commit, and this is basically, I'm committing these to my local repository. So I'm going to commit Fervent Noble to foo isn't J, because I'm really creative. And then I'm going to remove the containers. So Docker RM, Sadbanak, and Fervent Noble. And now I'm going to run Docker images. And it's going to be hard to read because of the number of thingies. Let's do that. Okay, so this is what that starts to look like. So the repository, I have a repository called foo isn't J. I've got a repository called foo is J. There are tags, there are image IDs, there are sizes. You'll notice these are about the same size. So now what I want to do is let's just restart. I can start a container from one of these. So Docker run, let's use foo is J, bin bash. There's J. And if I look at the other one, I'll see the same thing. Now, let's do a Docker history on foo is J. So foo is J has that base layer, but then on top of that, it's got, well, a command that's kind of a no-op, adding bash, but then it's got 4 bytes. Let's look at the Docker history on foo isn't J. Oh, look, it's got that middle layer, but then it's got 16 bytes, and so that's where they differ. And it's kind of neat. I can basically, so I've just done Docker history, and it shows me like the history of a container, the history of an image. Docker's, one of the other things is, and LXD does this too, I'm going to run Docker inspect and say I'd like to know a lot about foo is J. And what I get is, hey, here's all this information. Oh, wait, and it's in JSON. Okay, so let's do that with an actual container. Okay, so Docker inspect. Hey, command completion on that. Cranky Rosalind is our name now. And I give them even more information. What do I use the most on this? What do I use this the most for? Honestly, I use this mostly to get its IP address. The cool thing is when you start dealing with containers in Docker, you end up being able, you can interrogate each of the containers. You'll end up with a pile of containers, and so you'll want to know, like, hey, what's your IP address? What's yours? What shared memory? What shared memory functions do we have? What do we have access to? And you can start linking them together, or you can massively keep them separated. In our case, my goal is to keep them darn separated. So the next thing I want to show you is a Docker file. And let's actually, I've made a few ahead of time. So a Docker file is meant to look very much like a make file. This is, if you can't figure out that developers really, really love this stuff, it's like created it, love it, live it, they do. So what a Docker file does is it says start from this base image. And then each of these commands is basically adds another layer and does some stuff. These commands are what I was seeing in Docker history when I was looking at the image. So this is take CentOS 7, run yum update, add a web server. Oh, and I'd like to also expose port 80, because otherwise none of the ports are available from the base operating system. And then entry point basically says I'd like to run this command. So that's my Docker file. I can build something from that. I can run Docker build, and I'm going to call this my image so I remember that it's an image, not a container. Okay, so all of those things are running super fast because, like I said earlier, Docker already knows. It says, I've started with CentOS 7 and run each of these commands before, so I know what to do to get to there. I've basically cached that. Now you can override the cache, but in this case, I really want the cache because I'm in a room and I don't want to have to rely on bandwidth. And once I've done this just now, if I'm going to go and build 6 more of these, well, then I'd like that too. So I build this thing, and now what I want to do is basically say, let's look at Docker images again. We have my image at the top, so let's run it. Okay, Docker run, instead of IT, I'm going to say D, which puts us in the background, daemon mode basically. Name, I'll call it my container, and I'll start it from my image. Okay, I've now got that running. So let's find out what the IP address is on my container. So Docker inspect, my container, it's going to be 17054. So let's go into the virtual machine that I've been SSH'd into. And 172.17.0, what was it, 54? And there's my web server. This is a web server that's running inside the container. I can enter the container and go take a look at it. So if I want to enter the container, I was doing an attach. So let's do that. Let's, or rather, instead of doing the attach, because I don't have a terminal, let's just add one. So I'm going to add a process to the container. Okay, so Docker exec IT, my container, and let's add a shell. So now my container is my Apache web server and all of its processes, and my shell. And I can be looking around here and basically saying, okay, oh, I must not have a netstat in here. Well then, but this is what I've got going in the container. What I can do at this point, let me just kind of move forward. I'm going to exit out of that container and I'm say, wait, what if I actually want to expose that port? Not just to the Linux machine, because I had to go into my RHEL 7 box, and I'm on my Mac, and I don't want it to be like that. I just want to be like using the browser on my Mac. That seems easier. So I'm going to run publish 8123 to port 80. So what I'm saying is basically, hey, I'd like to start up another image, and let's call this one my web server. So I'm going to start up another container from that image, and I'm going to say, hey, so the port 80 on that, I'd like that to be port 8123 on the host. Okay, and so that's running, and so I'll bring up my handy-dandy Chrome on the Mac, and RHEL 7, 8123. Okay, cool. So now I've got access to the web server that's running on that container just by going 8123. So so now I've got a problem. There's no syslog running in there. But it's not just that. It's that I've got my own syslog, and I don't need to actually have a separate syslog inside the container. So, but if I want to do that, this thing's going to be access to devlog on the host or outside of the container. So basically what I can do is I can say, okay, Docker run, and I do the same stuff I was just doing, but let's do this. Let's do Docker run, and I'm just going to start up a new container from foo.is/j, but I'm going to say I'd like devlog on the host to be shared as devlog in the container. So foo.is/j bin bash. So now I'm in the container. Let's just run logger. Okay. Control PQ. Tell to var log messages. And there's my okay. And so there's my log. And that's how I'll do it. Now that volume mount actually extends. Oh my God, I'm having the most fun time with the projector right now. Blame the projector, Jay. I want my slides back. And I'm too dumb to figure it out because I'm in presentation mode where you lose a lot of IQ points. And you rely a heck of a lot on the people out there to be like, you mistyped that, dude. No, it's the other one. And you're like, oh, thanks, guys. So this is volume mounts. Basically, you can take a directory or a file or a bunch of them one by one and share them in. And that's kind of how you handle the fact that you've got this containment happening. So I'm going to do a little bit, I'm going to kind of break off of demo a little bit right now and just tell you some more. So Docker basically starts maintaining its own IP tables rules. And I like this a lot. You can actually turn this off and tell it that you'd like to write all of the IP tables rules yourself. It also defaults to not letting the containers talk to each other on the network. It creates IP tables rules that say any container can't talk to any other container on the bridge. And so you can basically, what you get is some cool IP tables rules out of publishing ports. And you get NAT rules and so on. And so when we were publishing a port, what we ended up getting was some DNAT rules for free. So what else? The next thing I want to do is a container without root. Arrgh! I'm sorry, was that my outside voice? Okay, so I've got all these, I've got the containers I'm running, but let's make a new Docker file. And I can diff Dockerfile 3 against Dockerfile 2 so you can see what's changed. What I'm going to do now is I'm going to take a Dockerfile and say I'm going to expose, instead of exposing port 80, I'm going to expose port 8000. And I'm going to run some commands that the Apache user owns some files instead of root. And so now I'm going to do Docker build, and I'll call this one web unpriv, and I'll build it. And it's going to take slightly longer because it doesn't have these things cached. And I've just said expose 8000 and change the permissions on a few files. Okay, and now I'll run docker run -d for daemon. P, I'm going to expose port 80 on the RHEL 7 system. To port 8000. I'm going to run this and say this is going to run as user Apache. And so now, this one is called Elated Corona. So I've got Elated Corona. Let's go and take a look. So I was looking at RHEL 7 8123 before. And there's RHEL 7 on port 80. So this is running, so right now I'm serving to port 80 on my host. But if I look at the container, let's go take a look at it. Okay, docker exec, it, and what was this thing? Elated. Bin bash. Okay, look, that's not a root shell. I'm running as user Apache. Oh, heck, everything's running as user Apache. So this is where I get, this is the kind of thing I'm starting to get excited about. I'm like, wait, the whole container, basically Apache didn't, like before, Apache was doing what it does normally on your system. It starts as root, and it spawns, it grabs port 80, it spawns a bunch of workers, and they all don't run as root. And you say, okay, if an attacker busts one of those workers, you hope that they can't somehow get to the master and turn that into root access. Well, this thing didn't start as root, it started as unroot, and actually in the container they're in, root basically isn't there. I won't find anything running as root because everything in the container starts as Apache, the whole container's Apache, bust a shell and you get user Apache. You don't just get user Apache, you're stuck in this little funky file system that isn't the real hosts, and if there are other containers running on here, well, you're not in those either. And you don't have anywhere near as much network access as you might have had before. So before the container, like, what's one of the first IP tables rules that, like, if you ever look at the vendor or even your own IP tables rules set on a Linux machine, what's one of the like, most critical? It seems like you always have to have this rule. Localhost. Everything on localhost can talk to localhost. What does that mean? It means that any program on the box, if compromised, can talk to any other network available program on the box. Arrgh. So the point here is we're now able to start creating firewall rules around individual processes. We take a process, we stick it in a container, the container gets its own IP address. That IP address is that program's only way to the internet, its only way to the LAN. You throw on IP tables rules and say, okay, this process, only these IP addresses can reach it, it can only reach these IP addresses, And now you start getting things that we all want to do with our DMZ, like down to not just on the system, but now down to on the program. And that's where shit starts getting real fun for me. So I'm going to try and make up a little bit of time by taking us back into slide mode. So the next thing you can do is you can basically say, hey, I want to start dropping capabilities. And so I can say that the entire container, the same way as I said the entire container is non-root, if you do need to run as root, then you can say, well, the entire container basically is root, but it only gets these capabilities. We can do whitelists, we can do blacklists. I'm a big fan of the whitelist. You can basically say the only reason that Apache needed root access was that it could bind to port 80. Cool, you can have just one capability that lets you bind to port 80. Otherwise, you're running as user root and you can't actually modify any files in the file system unless they're owned by root. And that's really, really fun to watch root be like, oh, sorry, don't have access to that file. It's owned by user Apache. And you're like, okay, fine. So anyway, so the capabilities dropping is really neat. The nice thing is Docker drops everything by default except for this list, but I really like making it a much, much smaller list. Here's your exercise. Start a root container, try an iptables command, watch it not work. So you can use cap drop, cap add. The next part is that on rel, so on an SE Linux system, they do the same thing with LXD, with AppArmor. You end up with a profile. You end up with your types. And what happens on SE Linux, I'm walking right out of the frame, and I'm going to deal with that. So every container that runs with an LXC type instead of all the different types that programs would run at. But they each get their own compartment. They each get their own MCS compartment set. And so you're able to say, okay, at the file system level, one container can't touch another container's stuff. Obviously, people were really going for platform as a service here, but you can use that too, and I really enjoy that. The nice thing is that if you want, you can actually specify whatever SE Linux context you want. So if you create some SE Linux context for a given program and you want just that, you can say, okay, that's what this container runs as. If this container only runs Apache, I don't need it to run with svert, LXCnet. I can just say I want it to run with svert, LXC, Apache only, and get something that's even more locked down. And you end up with much, much easy. And actually, honestly, if you wanted outside the container, the whole system could be frickin' running unconfined. And then inside the container, the thing that's actually going to talk to the network, you end up having something that's really, 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 really tight. Again, it's just like, wow, if I can chop the system up, I'm not going for multi-tenancy. If I can chop the system up and make it so that my attacker, I guess I am going for multi-tenancy. I'm saying that I'm on the system and my attacker's on the system. And I'd like to keep us away from each other. Well, at least I'd like to keep him away from me. I'd like to screw with him as much as I like, and I will. So the next thing is, as long as you've got this container action going on, you have OSSec. You have the ability to start doing IDS or IP, to do IDS, either host-based or network-based, but I'm going to choose host-based. Cool thing is network-based, like, oh, okay, well, I could just, on this system, I could be running Snort outside if I like, and I can have it just watch the container's network interface, and I can see what's going in and out of that. I'm not going to, that starts giving me something. OSSec, how would I do this? You have two options with OSSec. You can either run OSSec outside of all of your containers and have it watch the logs, and given that it's kind of like a log-based IDS, that's really, really powerful. But then you're like, well, wait a second, what about watching all the files? Okay, watching all the files, that's actually kind of done better inside the container, but then I've got something that's running with a given level of privilege, and I have to figure out, so I could volume mount it. It's a tricky thing, but the primary purpose with OSSec where you're watching logs, you can do this with containers and you can have a whole pile of containers. And the great thing is that OSSec is actually most powerful when you're aggregating, when you see lots and lots of data. So if you've got a system and that system's got 20 containers running on it, there you go. Let's do something else. Gosh, I'm running low on time and so I'm struggling to figure out. Take this exercise and do it. It's really freaking cool. Just basically take your one image and spin up, say, 20 containers and watch them all boot up in about 3 to 5 seconds. And then they're all running and you're like, this isn't like running 20 VMs on one machine. Like, I've got 16 gigs of RAM. I can't get 20 VMs. Well, maybe I can get 20 VMs, but I can't get 2,000. And if you want, you can get 2,000. And so this is the first time I'm giving this talk, but the next time I do it, I want to do it with a Raspberry Pi and see how many containers I can get running on a Raspberry Pi. I'd like a good 100 of them, because I don't think you're going to get that many VMs on it. Okay, so I've also included a whole bunch of information for you. One of the cool things with Docker is it's got amazing man pages. It's really, really, really well documented. And now I'm going to talk about LXD in a lightning talk format. So, LXD is actually supposed to be pronounced LXD. It's basically a canonical's answer to this. It ends up using containers. It ends up looking a lot like Docker. It uses containers that run a lot more programs, but it doesn't have to, because they can run whatever you'd like it to run. Here's how you launch your first container. You're going to notice that the syntax looks a whole lot like Docker. It didn't start out that way, but it ended up that way because, well, you got a whole bunch of people using Docker, and they want to actually have things look the way they look. It ends up being slower. You don't get any caching, but you can say, I want to launch that image. It gets pulled down from the central repository at linuxcontainers.org, and now you're running. So once you've pulled down some images, this is what your image list might look like. LXC image list. You can say LXC image list and say, show me from a remote LXD server, and actually LXD ends up being a little bit more powerful than Docker, and in essence where you can have 5 different systems that are all running LXD, and you could take an image, pull it down from one, push it up to another, and actually start running commands against them. So we can do the same kind of things we did with Docker Inspect with LXC info and with LXC config show. You're going to notice that you end up getting YAML and you end up getting JSON. This LXD actually pulls in a REST API that is fully documented, and it's really neat because somehow the commands all kick out YAML, but the REST API all kicks out JSON, because JSON's the only way to put anything in storage, because XML is way too old. You do the same thing, Docker exec, now you're an LXC exec, run a shell. Look, when we look at that shell, we see a lot more processes. The model in LXD has basically been lightweight virtual machines with all the pieces. You can do them Docker style. So we've had a lot more processes. We notice root things running, but the cool thing is that LXD is actually running user namespaces so that you've got a root in there, but it's not the same root as in the file system. It's a root with a totally different UID. And that's really, really neat. So the other cool thing that you get out of containers and that get especially easy in the LXD model or the LXC model is you can snapshot a container. So you can take a container, you can snapshot it, you can go and run some commands, you can restore. You can take that snapshot, you can publish the same way we did with Docker where we were committing in LXD, we publish, and then delete the original container. You've got that image. The cool thing is that once you can publish, you can go and say, I'd like to take that thing I committed and push it up to another LXD server. So you push it up to another LXD server and then launch that server. From here, you launch a container on that server over there and start running commands on it as if you were over there. I know it sounds like SSH, but this is actually built right into the whole, you've got like an orchestration framework, and it ends up being really, really neat. You've got AppArmor and SE Linux and LXD. It's very, very similar. They already did the same kind of thing. I freaking love AppArmor. I like SE Linux too, but the cool thing is you can start saying, for that container, I want this profile. You get capability dropping just the same way, so you can basically create a container in LXD that only has one thing. Stop. You can firewall. There's my wrap-up slide. Thank you very much. Yes! Finished our time!